Oh. I feel like I found you, and in this video I hope I help you find you too. We are learning a very valuable technique, and that is the U-substitution technique that's used for integrals. Okay, this is going to be so great. And I'm looking at the same ones we did in the last video, but with this technique involved. See how it works. And it's all about finding U. Okay, so how does it work? Take a look at the first one. Cosine of x squared equals 2x dx. Well, since I can see the u here is, I'm talking at, okay, I'm looking for an antiderivative that when I take the derivative of it, I get back to this function. Well, I can always see here that if I took the derivative of x squared, I'm going to get 2x. And that is how we're going to help us find u. So in this problem, let's let u equal x squared. Then what that implies is we can differentiate both sides and say that du would be 2x dx. So we're taking the derivative of both sides with respect to x. So then it would be du dx is equal to 2x, and then I'm just going to multiply that dx the other side, and that's how I'm getting du equals 2x dx. Go through a little bit slower on that first one, all right? So then what happens is we can rewrite this as what's the integral of cosine of u, and then notice that 2x dx is du. And it's just a different variable. So notice what's the integral of cosine of u? Well, that's going to give us sine of u. And then from there, plus c. And then we just replace u back in. Since u equals x squared, we just plug that back in, and we get sine of x squared plus c. And there's your answer. So by using u, we can actually work with a lot easier integrals. This is a lot easier to work with than this is. And they're saying the same thing with just a little technique of u substitution. And if you wanted to check this, right, the derivative of sine of x squared, because it's always important you check, well, that would be the derivative of the outside, leaving the inside, times the derivative of the inside. And notice, and then the plus c would be plus 0, you get cosine squared 2x, and that works. Look at the second one. We had 3x squared times e to the x cubed, where I can see that x cubed, when I take the derivative of that, is going to give me 3x squared. So let's let u equal x to the third. Right, finding u is the tricky part, and it will take practice until you build into what your eyes are looking for. And what that is going to help us with is then du is going to be 3x squared dx. When I take the derivative of this side with respect to x, which again, I showed the work up there when you take the derivative with respect to x, and then you bring the 2x to the other side, but what you get is 3x squared dx. Well, I can rewrite this integral then as the integral of e to the u, and then the 3x squared dx is du. This is the same thing as this, just with a little substitution. And what's the integral of e to the u? Well, the integral of e to the u is just e to the u and then plus c, because the derivative of an exponential e, base e, is the function itself. And then you replace u with x to the third, and what we'll have is e to the x to the third plus c. And there you go. And if I wanted to check that again, what's the derivative of this function? Well, what I get is it's the function itself times the derivative of the inside, and notice that's what I got over there. Good. Look at part C. I can see here that the derivative of 5x to the third minus 1 is 15x squared, so that's going to help us when writing the antiderivative. So let's let u equal 5x to the third minus 1. And I'm not including to the third power, because you're going to see when it's u to the third, we can do the integral of that pretty easily. And then du is going to give us 15x squared dx. And that's great, because I can see that that's going to fill in this part of the integral. So I can rewrite this integral as u to the third du. U to the third would be 5x to the third minus 1 to the third. Du is the 15x squared dx. And the integral of this, well, that's just u to the fourth over 4 plus c, which replace u now, and what we're going to get is 1/4 5x to the third minus 1 to the fourth plus c. And there you go. There's the next one. And if we were to check that, you can see taking the derivative, I'd bring that to the front, making that a 1. Leaving the inside, you subtract 1, which is good. And then the derivative of the inside there would be the 15x squared, which we have there. So that's great. Now watch U-substitution on a little bit more complicated problems on D, E, and F here. Well, I see that sine squared, so typically chain rule, you have to work with the highest power. And the derivative of sine is going to give us cosine. So in this problem, a little bit trickier, and it's okay if you make a mistake. You'll know if you make a mistake because the u and du's, it'll be hard to rewrite that original integral. So let's let u be, and let me show you. Let me just show you the mistake. What if you said, okay, I want u to be 3x, and say you make a mistake, and that's okay. And then du would be 3 dx. Well, if you tried rewriting this, you would have cosine of u, sine squared of u, and then you don't even have a 3, so you have to have a 1/3 du to account for the 3 that would have popped in. And notice taking the integral of this is just as complicated as that. So this didn't help us. And that's okay. It's about finding the u. You'll get faster with time. So let's try this. Let's let u equal the sine of 3x, because I can see that all of that's being squared, and with chain rule, that's squared because we have to do the derivative of the inside later. It's going to come in handy. Well, the derivative of this, well, the derivative of the outside, leaving the inside alone, times by 3. Okay? And then all of that is dx. Now, how do we rewrite this integral? So then it would be the integral of sine of 3x is u, so it's going to be u squared. And then we have the cosine of 3x dx, so that's your du. But notice that we have an extra 3 in there. So we have to account for that by putting a 1/3 in front. So that way, if we were to rewrite this, we would have sine squared of 3x, cosine of 3x dx times 3, and that 1/3 make sure it doesn't show up. So now this is the same as that. And again, remember that that's the same as doing the integral of 1/3 u squared du. So then I could write this as 1/3 u to the 3rd over 3 plus c, right? And then just replace my u with sine of 3x, and what I'm going to get here is 1/3, well, it's actually going to be 1/9 sine cubed of 3x plus c, and there's my answer. And it's a little bit faster where you're just following a technique rather than having to do as much thinking, if you pick your u correctly, that is. And if I check this, now I'm running out of room, but that's okay. The derivative of this would be the derivative of the outside, so you'd have 3/9, leaving the inside alone, and that would come down to a 2, sine squared of 2x, times the derivative of the inside, which would be cosine of 3x, and then timesing the derivative of that, which would be 3. And notice that 3 would make that 9/9, and then we have sine squared of 3x, cosine of 3x, which is exactly what we got there. So that is correct. Good. What about E? Okay. Same problem as the last video, and we can see that the derivative of this will give us x plus 2. So let's let u equal x squared plus 4x plus 2, which would imply that du, if we take the derivative of both sides with respect to x, will give us 2x plus 4 dx. All right. Now that doesn't help us necessarily see this, so let's rewrite du as 2x plus 2 dx. Okay. So if I'm trying to rewrite this integral with u now, I would have the integral of u to the 5/4, and then I have the du, which is the x plus 2 dx, but since there is a times 2, I have to account for that, and I'll put a 1/2 in front to account for the 2 that I created with the du. So then I can pull out the 1/2 and do the integral of u to the 5/4 du, which I can just add 1 there. So then I'm going to get u to the, adding 4/4 would be 9/4. And then you divide by 9/4, and then plus c. Okay. Dividing by 4/9 is the same as multiplying by 4/9. So I'd have 1/2 times 4/9 u to the 9/4 plus c. And then, plugging u back in, I'm going to have 4. Well, that's a 1 and that's a 2. So let's actually write this as 2/9 u, which was x squared plus 4x plus 2 to the 9/4 plus c. And there's our integral of that function. Okay. And I believe that's what we got in the last video. Let me just make sure. It was 2/9 x squared plus 4x plus 2. Yeah, okay, good. And then the last one. So maybe it's not as easy to see. You might be saying, okay, I take the derivative of this, and if I take the derivative of this, I would have a 4 goes in front, which I get 12 over 2, which is 6. So I'd have 6x to the third minus 3. Well, 6x to the third minus 3, if I pulled out a 3, I get my 2x cubed minus 1, which is great because there's what I needed. So this is going to be my u here. So let's let u equal 3/2 x to the fourth minus 3x. So then when we take the derivative of this, bring the 4 in front, you get 4 times 3, which is 12 over 2, which is just 6, x to the third minus 3, and all of that dx. Okay. And then again, if that doesn't help you see how this is the original integral, let's pull out a 3 and write this as 3, 2x to the third minus 1 dx. So now we can rewrite this integral as a u to the fifth, and then we can say du, because we have the 2x third minus 1 dx, but to account for that 3 that we included, we just need a 1/3 in front. Okay. Solving for this integral, I'm going to pull out the 1/3, and you'll get 1/3 u to the 6 over 6 plus c. And then replacing u, what we'll have here is 1/18 3/2 x to the fourth minus 3x to the sixth plus c. And there it is. U-substitution, that technique. If I took the derivative of this, if I wanted to check, because I'm curious, because this one's a bit more complicated. Let's make sure we did this one right. All right, let's check this last one. The derivative with respect to x of 1/18 3/2 x to the fourth minus 3x to the sixth plus c. Well, then that 6 would come in front, so I'd have 6/18, leaving the inside alone. Bring that to the 5, times the derivative of the inside, which would give me, remember that 4 comes in front, so 4 times 3 is 12 over 2, so I get the 6x cubed minus 3 as the inside there. Okay, and then I can pull out a 3 on that one, so I'd have 6/18 3/2 x to the fourth minus 3x to the fifth times 3, 2x third minus 1. And that 3 times 6 is 18/18, which is great because that will go to 1, leaving us with that original function in the integral up there. So that's good. So that's u substitution. Find your u. You have to see the big picture. What is it that when I take the integral, is there a piece of this that when I take the derivative of this antiderivative that I'm trying to find, it's already in that integral. Okay. Hope that helps. Give it a go yourself and find your u. All right. Bye-bye.